Welcome to AI Paper Slop, the YouTube series where we summarize the latest, most crucial AI and tech papers so you don't have to spend your entire weekend, parsing equations.
Yeah, let us do the heavy lifting for you.
Exactly. If you're an ML engineer or an AI researcher trying to keep up with the bleeding edge, you're definitely in the right place. So today we are jumping straight into a paper called Sugar. That's a scalable, human, video-driven, generalizable humanoid loco-manipulation.
Quite a mouthful.
It really is. This comes from researchers at Peking University and Beihang University. And right off the bat, here's the bottom line. Sugar is this three-stage, data-driven framework that basically teaches humanoid robots, specifically they use the Unitree G1, how to perform complex whole-body loco-manipulation tasks purely from unannotated human videos.
Right, so we're talking about walking and interacting with objects at the exact same time.
Yeah, exactly. And it extracts this noisy kinematic data using vision language models and segmentation. Then it refines that data into physically feasible skills using a privilege reinforcement learning policy. And finally, it distills it into a hierarchical diffusion policy.
Which is super elegant.
It is. And the result is zero-shot sim-to-real transfer, meaning it moves from simulation to the real physical world without needing to be trained on the actual hardware first. And it does all this without that agonizing task-specific reward engineering we usually see. It just scales in performance by feeding it more unstructured video data. So, okay, let's unpack this.
Yeah, to really appreciate the scale of this breakthrough, we kind of need to look at why whole-body loco-manipulation is considered like the absolute holy grail of physical AI right now.
Oh, absolutely.
It basically represents the compounding difficulty of maintaining dynamic balance,
yeah,
the locomotion side of things, while simultaneously executing these contact-rich interactions with objects.
Because it's the intersection of two totally different physics problems, right? Because if the goal is just getting a robot to walk across a room, that is essentially a solved problem. We have robust controllers for that.
Yeah, Boston Dynamics solved that a while ago.
Right, and if the goal is getting a robot arm that's just bolted to a heavy stationary table to pick up a cup, that's also highly optimized.
Very standard.
But asking a bipedal robot to walk over to a heavy box, bend its knees, shift its center of mass, pick up the box, and walk backwards without falling over, the physics of combining those two domains are just an absolute nightmare.
It really is, because the center of mass is constantly shifting, and the contact forces with both the ground and the object are just highly dynamic.
Yeah.
Until this paper, the field has sort of been trapped in this scalability bottleneck.
Yeah.
The industry has basically relied on three major paradigms, and all of them carry these, fatal flaws when you try to scale them to general-purpose humanoid assistants.
Right, so let's contextualize those flaws for a second. Imagine trying to teach someone to play tennis. Paradigm number one, reinforcement learning from scratch, is like dropping them on a court yelling, "Score points!" and just letting them flail around for 1,000 years in simulation until they accidentally hit the ball.
That is a very accurate analogy.
Right. You get impressive single-task results eventually, but the fatal flaw is the reward engineering.
Well, the reward engineering is a nightmare. You have to write these agonizingly specific, mathematically heavy, per-task reward functions. If you just define the reward as, get the box to the table, the RL agent will find a million ways to technically achieve that while completely exploiting the physics engine.
Yeah, or breaking its own simulated legs.
Exactly. It might just punt the box across the room. So shaping the reward to force the robot to walk naturally, grasp gently, and lift safely, that requires hundreds of hours of manual tuning per task.
Right. And then you have the second paradigm, which is reference motion tracking. So going back to our tennis analogy, this is like forcing the player to swing the exact same way every single time, regardless of where the ball actually is.
Yeah, it's super rigid.
You record an interaction, usually through some really expensive motion capture suite, and you train the policy to rigidly replay that exact trajectory. And sure, it looks incredibly natural, but it rigidly binds the policy to that specific recording.
Right, which means it can't adapt. If the box is placed 5 inches to the left of where it was in the recording, or if it has a slightly different geometry, the policy just fails.
Yeah.
It has basically zero ability to generalize.
Which leaves the third paradigm, right?
Yeah.
Teleoperation.
Yeah, teleoperation. Mm-hmm. And this produces fantastic data because a human is actively piloting the robot. So the data is perfectly consistent with the robot's specific physical embodiment.
But it's fundamentally unscalable.
Completely unscalable. You just cannot practically collect millions of hours of teleoperation data because it requires highly specialized hardware. like VR rigs or those really expensive exoskeletons, and massive amounts of human effort.
It's basically the equivalent of manually grabbing the tennis player's limbs and physically moving them through a perfect swing for every single practice shot.
Yeah, exactly. None of that scales to the sheer chaos and diversity of the real world. And that is exactly why the researchers behind Sugar looked at the internet.
Right, because the internet is already overflowing with unstructured videos of humans interacting with objects. It's this naturally occurring, infinitely scalable data set.
But that introduces a massive technical hurdle, right? Because human video is just 2D pixels. It's incredibly messy.
Oh, yeah. Monocular video is a nightmare to parse.
So how do they actually turn a compressed YouTube vlog into actionable 3D robotic data without manually annotating every single frame?
Well, they engineered a fully automated extraction pipeline to just bypass manual labeling entirely. So they break the video down into 3 streams: the human, the object, and the contact between them.
Right.
For the human, they use a tool called SamBody. But they don't just draw bounding boxes. They project the human into 3D space. They map a skeletal structure onto the 2D image, align it with the depth observations of the scene, and optimize it using an algorithm called iterative closest point.
ICP, yeah. To ensure the spatial accuracy is locked in.
Exactly. So you end up with this rough 3D trajectory of the human's joints over time.
And then they have to track the object. So they generate a 3D mesh of the object using a segmentation model, figure out its real-world physical scale by aligning that mesh with a point cloud of the environment, and then use foundation pose to track its 6D pose over time.
And just to clarify, when we say 6D pose, we mean it's tracking not just the X, Y, and Z position in space, but also the pitch, yaw, and roll, like exactly how the object is tilted and rotated.
Right, so we have the human moving and the object moving. But the pipeline is still missing the single most crucial piece of loco-manipulation, which is contact.
Right, because a 3D model doesn't inherently know when a hand is actually applying force to a box.
Exactly. So to solve the contact problem without paying armies of human labelers, they integrated vision language models. Specifically, they use Qwen3VL.
Oh, Qwen3VL is fantastic.
It really is. They feed the raw video frames to the VLM using a highly constrained prompt template. They're essentially using a language model as a physics verifier. They ask it, is the specified body part in direct physical contact with the object? Answer yes or no. Do not infer based on intention, only actual physical contact.
But wait, video has severe depth ambiguities, right? Like if
Yeah.
the robot is supposed to kick a box, from the camera's perspective, the foot might be completely hidden behind the box at the exact moment of impact.
Yeah, occlusions are a huge issue.
The VLM just can't see the contact.
Right, so for heavily occluded tasks, they fall back on a really clever physics heuristic. They infer contact if the object's velocity suddenly spikes above a certain threshold.
Ah, that makes sense.
Yeah, if a stationary box is suddenly moving at 2 meters per second, it's safe to assume the foot made contact. And then they apply temporal filtering to smooth out any flickering in those binary labels.
Okay, so the output of this entire extraction phase is what they call kinematic interaction priors. It's basically a raw data set consisting of body trajectories, object 6D poses, and binary contact events.
Yep.
Okay, but playing the skeptic here, any ML engineer is immediately going to spot a glaring issue. A human body and a Unitree G1 robot have vastly different kinematics.
Vastly different.
The robot has different joint limits, a totally different weight distribution, and fewer degrees of freedom. And on top of that, extracting 3D data from monocular 2D video inherently creates artifacts. You are going to get data where the human hand appears to be clipping directly through the solid geometry of the box. If you feed that physically impossible data into a standard physics engine, the math literally explodes. The collision forces just go to infinity. So how is this extracted data actually usable?
Well, what's fascinating here is the authors explicitly acknowledge that severe limitation. They call these priors imperfect, right in the text. The data is full of occlusions, contact artifacts, physical implausibilities. But their core insight is that despite all that mathematical noise, this extracted data perfectly captures what they call the coarse but complete task logic.
Right. It basically tells the story of the task.
Precisely. It outlines the rough approach trajectory, the sequence and timing of contact events, and the resulting movement of the object. It defines what the interaction is actually trying to accomplish.
Okay, I see.
If you forced a robotic policy to directly imitate these noisy kinematics, it would crash immediately. So Sugar doesn't use this data for imitation. It uses this messy logic simply as a seed for the next phase.
Which means they need a translator. They need a way to take data that defies the laws of physics and force it to obey gravity, joint limits, and contact dynamics.
Enter the refiner.
Yes. This is where the refiner comes in. So the refiner is this privileged reinforcement learning policy trained purely in simulation.
Right, and we call it privileged because during this phase, the policy has access to the ground truth, God mode state of the simulation.
It knows everything.
Yeah, it knows the exact mathematical mass of the object, the exact friction coefficient of the floor, and it has pristine, noise-free coordinates.
And they train this refiner using a unified mimic-style reward. So it looks at that noisy, clipping, physically impossible video prior, and it gets rewarded for achieving the same general goal, the same object movement, the same contact timing.
But it is forced to accomplish that goal while strictly adhering to the physics engine.
Right. It's like a physical therapist looking at a sloppy, fast-forwarded video of a golf swing and forcing the patient to adapt that swing to actual human joint limits so they don't, snap their spine. It refines the sloppy reference into a high-fidelity skill.
That's a great way to put it. Training that refiner, however, introduces a massive instability problem regarding initialization.
Oh, the initialization crisis.
Yeah. In standard reinforcement learning, you generally initialize an episode in one of two ways. You use start state initialization, where the robot always starts at the very beginning of the task, like standing 5 feet away from the box.
Mm-hmm.
Or you use reference state initialization, where you pick a random frame from your reference data and start the robot in that posture.
But if they use start state initialization, the robot might spend millions of compute cycles just learning how to walk up to the box, fail the grasp every time, and never actually get to practice lifting or carrying it.
Right. It's massively inefficient.
And they can't use reference state initialization because, as we just established, the reference data contains physically impossible states.
Exactly.
If you initialize the simulation in a state where the hand is clipping through the box, the physics engine will immediately fail the episode.
So to solve this initialization crisis, they developed the Progressive State Pool, or PSP. As the refiner policy begins training and occasionally succeeds at reaching new, physically valid postures, maybe it manages to approach the box and make contact without crashing the system, saves that exact simulated state into a massive pool.
Oh, I love this part. It is exactly like using save states in a brutally difficult video game.
Yes.
Instead of making the robot restart the entire level every single time it drops the box, and instead of dropping it into a corrupted boss fight it has no context for, the progressive state pool creates these verified checkpoints.
It allows the robot to practice the middle and end parts of a task, like the lifting phase, from a diverse set of starting postures that the policy has already mathematically proven it can safely reach.
And the ablation studies in the paper demonstrate just how vital this is, right?
Oh, yeah. When the researchers removed the refiner entirely from the pipeline, the success rate for carrying a box dropped from nearly 70% down to roughly 41%. It completely tanked.
Wow.
Furthermore, when they kept the refiner but removed the progressive state pool, reverting back to standard initialization methods, they saw noticeable performance degradation across all tasks. The progressive state pool is the stabilizing mechanism that makes the refiner work, acting as the critical bridge across the sim-to-real gap.
Okay, so we now have this beautifully refined, physically sound set of skills living inside a simulation. But we still have a fundamental deployment problem.
Right, the God mode problem.
Exactly. That privileged policy relies on God mode simulation data. A real Unitree G1 robot standing in a real physical room does not know the exact mathematical mass of the box it's looking at, and its onboard cameras are full of sensor noise. We have to distill this perfect simulation policy into something that actually survives the messy real world.
And this is achieved through the final stage, distillation into a hierarchical autonomous policy. They take the physically feasible demonstrations generated by the refiner and distill them into a two-part architecture. It basically divides the cognitive load into a System 1 and a System 2, much like human psychology.
Right. So the command generator acts as System 2. This is a high-level diffusion policy operating at a relatively slow 10 hertz. And we should probably explain diffusion here.
Yeah, that's a good idea.
Usually we associate diffusion models with AI art generation, right? Starting with static noise and iteratively refining it into an image. But in robotics, instead of outputting pixels, the diffusion policy takes in the robot's proprioception, its internal sense of where its joints are positioned, and its visual observation of the object.
Right, and it uses that noise reduction math to iteratively generate a smooth sequence of future joint positions from a cloud of mathematical possibilities.
which allows it to handle multimodal possibilities. If there are 3 valid ways to reach for the box, a standard model might average them together and just miss the box entirely. But a diffusion policy can definitively select one clear fluid path.
Exactly. The generator predicts an 8-step sequence of those target joint positions. But to maintain a balance between long-term planning and immediate reactivity, it only executes the first 4 steps before it completely replans.
And waiting below that is the command tracker, which is System 1. This is a low-level policy running much faster at 50 Hz. It takes those 10 Hz target commands from the generator and robustly tracks them, turning the high-level intent into actual physical joint torques using a standard proportional derivative controller.
If we connect this to the bigger picture, this perfectly mirrors human cognition when interacting with the physical world.
How so?
Well, the command generator is your conscious mind deciding to lift a heavy box. It plans the overarching trajectory of your arms and torso. Meanwhile, the command tracker is your subconscious fast-twitch muscle system.
Oh, that makes total sense.
Yeah, it operates at a much higher frequency, constantly adjusting your ankles and knees for microslips, friction changes, and balance variations without you ever having to actively think about it.
Right. And what makes this architecture incredibly resilient is that the generator is trained on the states the robot actually encounters during execution, not just idealized simulation path. It creates a closed-loop system.
Exactly.
If the low-level tracker starts to drift because, I don't know, the physical floor is slightly slippery, the high-level generator sees that unexpected state, recognizes the error, and proactively outputs a new command to pull the entire system back on track.
And, theory and simulation are fascinating, but the ultimate validation for this audience is hardware deployment.
Yes. Does it actually work on metal?
It does. The researchers deployed the distilled sugar framework onto a real Unitree G1 humanoid robot and tested it across 6 varied whole-body loco-manipulation tasks: push box, pick bottle, carry box, sit chair, and kick box.
And it vastly outperformed baselines that rely on rigid reference tracking. But here's where it gets really interesting for me. We need to look at the scaling laws, because that is the ultimate aha moment for an ML engineer.
Oh, absolutely.
Because this is a data-driven framework. The researchers trained their model using varying amounts of unstructured human video data for these physical tasks just to see what would happen.
Right. They tested the physical deployment using 20 video trajectories, then 50 trajectories, and finally 100 trajectories per task.
Okay, and the numbers are wild. When they fed the system just 20 human video trajectories, the success rate on the physical robot was 31.6%. When they increased it to 50 trajectories, the success rate jumped to 66%. And when they fed it 100 trajectories, the success rate hit 86.4%.
I mean, that is the exact trend line you want to see. By simply increasing the volume of messy data, the coverage of the state action space inherently expands. The architecture naturally distills more robust, generalizable behaviors without requiring any algorithmic intervention.
Right. They achieved a massive jump in physical reliability without writing a single line of new reward code. They didn't have to meticulously re-engineer a math function for a new edge case. They just threw more unstructured human video into the pipeline, and the robot inherently got better at its job.
It's incredible.
It is the bitter lesson of AI, right? That compute and data scaling ultimately trump manual engineering. And here, it's applied perfectly to humanoid robotics.
And that underlying robustness translates visibly into physical resilience. One of the most striking aspects of the paper is the visual evidence of what they term autonomous failure recovery.
Oh, I watched the video for this. It's so cool.
Right. They show videos of the Unitree G1 bending down to pick up a heavy water jug. And during the motion, a human researcher actively interferes. They shove the robot's torso, they grab the jug, and literally rip it away from the robot's hands.
It's the classic robotics hazing ritual. You always have to kick the robot.
Always. But in traditional rigid control systems, that kind of external, unpredictable perturbation would cause a catastrophic, unrecoverable failure. The robot would either freeze because it lost the reference trajectory, or it would simply fall over.
But with sugar.
But with sugar, because of that hierarchical closed-loop system we discussed, the robot dynamically recovers its physical balance, replans its high-level intent, walks over to where the human maliciously moved the jug, and attempts the grasp again. It survives the sim-to-real gap under active physical duress.
It is honestly an incredible leap forward. The elegance of the sugar framework is its ability to act as a universal translator for the physical world. Unstructured, noisy, clipping, imperfect human video goes in on one end, and robust, scalable, real-world humanoid robot skills come out the other.
Yep.
It completely bypasses the historic bottlenecks of heavy mathematical reward engineering and unscalable manual teleoperation.
It proves mathematically that the underlying logic of a physical interaction is infinitely more valuable than achieving kinematic perfection, provided you have a robust reinforcement learning pipeline to refine that logic through physical simulation.
Exactly. Now, the paper does note in its limitations that sugar currently focuses on coarse-grained interaction skills. So we are talking about pushing large boxes and sitting in standard chairs. And furthermore, it currently uses state-based policy deployment, meaning the real robot still needs explicit object coordinates fed to it rather than processing raw visual pixels or language inputs directly at inference.
Right, that's the current limitation.
But I want to leave you with a final provocative thought. Imagine scaling this exact pipeline. If a humanoid robot can learn to dynamically balance, carry a heavy box, and recover from being physically shoved just by mining noisy YouTube clips. What happens when we scale this mechanism to fine-grained manipulation?
That's the dream.
What happens when this pipeline has the compute power to digest millions of hours of first-person GoPro vlog footage of people threading needles or chopping vegetables or playing the piano? Are we simply a larger compute cluster and a bigger video dataset away from a humanoid robot that can watch a 5-minute cooking tutorial and instantly know how to bake a cake in your physical kitchen?
The architecture to extract and refine that logic is here. Now it seems it's just a matter of scale.
Something for you to mull over. Thank you for joining us for this deep dive into the source material. Make sure to hit subscribe, and we will catch you on the next session of AI Paper Slop, where we turn tomorrow's ArcSoft preprints into today's insights.